Practical Guide to Optimized High-Quality Wavetable Oscillators. I'm Matt Tytel. I make a wavetable called Vital. There's the website right there. And there's my Twitter. That's my synth. It's Vital. It's a wavetable synth. Came out about a year ago, so it's pretty new to the industry. It has a free version, so you can download it. It has all the features built in, so you can try it out if you want. Let's get into my talk. So why give this talk about how to create wavetable oscillators? These are 9 different wavetable synths that are on the market right now. There's been a huge boom of wavetables recently. I don't know if anyone's missed that, but so why am I teaching people how to make wavetables when there's so many out there? I feel like there isn't a lot of information on how to create a wavetable. If you like search, how to create a wavetable, you need to like gather a bunch of different pieces and put things together, and you might not do it right. So what I'm doing is consolidating everything I learned creating Vital into a single talk, so it's all in like one place. So you don't need to, scrounge around for different ways to do things. All right, so first, what is a wavetable oscillator? I really hate slides, so I put a little sparkle whenever I have a demo to switch over to. So this is a basic idea of a wavetable. You have a waveform, and it's represented by a bunch of points in an array maybe, and you can play the waveform by like sampling it over time, and you generate a stream of audio that is basically just the wavetable repeated in time. So it's a really simple concept. You just give it a frequency and have the wavetable, and the output is a repeating pattern of your wavetable. So a really simple concept, but actually there's a lot of pitfalls when actually trying to create this. So just going to go over the implementation overview for wavetables. This isn't like the only way to create a wavetable, but I feel like it's what most people do, and I feel like it's one of the correct ways to do it. So the first step is to pre-process the source waveform. We'll go into why we need to do that in a second. The second is you update the phase, because there's, like you saw in that demo, in the last demo, you have a position where you are, and from that you'll get what samples you're between, and how far you're between them, and then you use that the sample index and the sample offset to interpolate your waveforms, because you might be between 2 samples, so you need to figure out what the value should be at any given moment. All right. So pre-processing the waveform. I'm going to go a little bit of background into Harmonics. I don't know if anyone was here in the last talk. It was an additive talk, so it might be a little bit of a repeat in theory, but let's go to a demo. Okay. So if anyone hasn't used Desmos, it's probably like one of my favorite websites in the last couple of years. But it lets you like do a bunch of math stuff. But so here I created a really simple wavetable. It's made up of 16 points at the top. So this is a really small wavetable, 16 points. And I am creating an interpolation line to just to go between all the points. So basically, what you see here is the wavetable we're trying to represent up at the top, and then at the bottom is a bunch of harmonics, and each harmonic is a sine wave, which is just like what we think of as a pure frequency in when we hear. And you have a bunch of harmonics, and each have an amplitude and a phase. So you have the bass fundamental here, and the second harmonic here, third harmonic, fourth harmonic, all the way down to the 8th harmonic. And when you add up these harmonics, you actually get this black waveform at the top that interpolates all our points. So basically, any wavetable can be thought of a sum of sine waves. We'll get more into that in a minute. That's just a little bit of background. I do want to talk, since this is, I showed that example with 16 samples, It's not really what we're going to be doing. We're actually going to be having a much larger wavetable in practice. I think just to mention, most synths I've seen do 2048 harmonics. So that's like from the fundamental, it goes up. It'll have 1024 harmonics, and which gives us, if you play a really low note like 20 hertz, it'll go up past the human range of hearing. So that's basically a really rich sound. So it's 2048. It's like a real. It's like a good number to pick. But you can create a wavetable any size. All right. I just wanted to mention that before we go on. So most of us have heard of aliasing before, and I have a couple examples up here of graphics aliasing at the top left. It's just a checkerboard, and it distorts as it goes into the distance. And on the top right is a circle, the edge of a circle, but it creates like these jagged patterns that are not quite what we want. And you may have heard that audio, when you go past a certain range, will reflect back down, and that's what aliasing is. And I'm going to, that's what this picture down here is, but let's take a closer look at why aliasing happens. This is an example function that we're going to be sampling. So in audio, in the digital world, we sample audio. So our original source is this sine wave, and then we sample it, and we get this form. And as we increase the frequency, I'll just let this run a little bit. We get to this point where the samples are going to be alternating up and down, right there, almost there, alternating up and down. This is the maximum frequency we can represent, and you can see it's like really fast, and it just alternates. That's what we call Nyquist. And once you go past that, I just want to go reverse a little bit. Okay, we're increasing our frequency. We're going to hit Nyquist, and then we see that the pattern actually just is now just mirrored and is now going back in the other direction. And if we keep running this, we'll see this sine wave emerge. But when we look at our original source, it's much a higher frequency. So this is where the term aliasing comes from, because this frequency is an alias of this sine wave that we see here. Okay, so we want to avoid that. We don't want to play any frequencies above Nyquist, which is that maximum frequency we could represent. Okay, so methods to prevent aliasing. If you this is one of the most frustrating things with searching how to do wavetables is how do I anti-alias? And you'll get these answers like you should use blit or blep or bloop or oversampling, and those are not appropriate for wavetables. Blit and blep are both for helping anti-alias a discontinuity or a so it's not really good for anti-aliasing an entire waveform, which might be have a bunch of discontinuities or no discontinuities. And people will always say, oh, just oversample and then downsample. That will mitigate the problem, but it's not a great solution. And I'll show you we have a better solution, which is band limiting the waveform with Fourier transforms. I'm not going to go into the theory of Fourier transforms, but I will go into how we can use them to band limit. All right, so this is just a very quick how-to with Fourier transforms, but it should be pretty simple, even though the theory might be more complex. So this is our 16 samples from our wavetable. It's just in an array. And the Fourier transform converts it to a list of harmonics we see here. And I want to go back to one of the demos in a second, but you notice that you have H0 through H8 here, so you get 8 harmonics out of a 16, 8 harmonics in a DC offset out of 16 samples. So let's go back to that demo I showed earlier, which is our waveform at the top and then a list of harmonics that were sum to that black waveform. This is actually a Fourier transform. I am computing these amplitudes of these sine waves and also some other values. So let me go into what each one is. So the first one is just the DC offset. The second one is the first harmonic. And you notice that there is like an amplitude of the sine wave, but it can also change. If I change these points, you can kind of seeing it shift left and right, so a little bit left and right there. So it also has a phase, and that's why there are, if you look at the Fourier transform, that's why it's actually, the harmonic one is actually 2 slots, because you need to represent both amplitude of the sine wave and how it's shifted left and right. And these values here are basically representing that. Don't confuse like amplitude and phase with what the Fourier transform actually gives you, which is the complex value, which is a Cartesian value. So the amplitude of this circle is the amplitude of the sine wave, and then if you see this, like where this angle is the phase. So, but this value gives like the xy of this point. Just, we don't need to know that for what we're doing, because we're just going to clear both of them out for certain harmonics, but keep that in mind. So we have DC offset doesn't have a phase, obviously. It can just have an amplitude, so that's why there's only one value there. Harmonic 1 through 7 both have amplitude and phase. Something weird, which isn't quite obvious, but I'm going to leave up to you to like think about a little bit, is that this last harmonic, the 8th harmonic in this case, it only has one amplitude. I'll let you figure that out on your own, or we can talk to me after. But it only has a single value. You can't have a phase with that one special case. And so that's why they cram it all the way on the left there, and a lot of Fourier transforms. So don't forget about that. Otherwise, you hear like a really piercing high harmonic when you do your Fourier transform, inverse Fourier transform. Okay, so the next step is just to clear. This is, I'm just picking a random cutoff here, so we'll talk about when to do that, like at what point to do this in a bit. But this is just if we want to say we want to band limit to up to H3 and like clear everything out. Say that they're going to alias because they're too high. We're going to clear. This is just one example of that. So we're going to clear H4 through H8 just by like clearing those samples in the buffer. And don't forget this one over here. Otherwise, you'll get a piercing sound. And then you do an inverse Fourier transform at the end, and you get a band-limited version of that. And it may look totally different than our waveform here. I can do a band limit here if I just cut these out. So it may look like totally different than our original waveform. Okay. Okay. When do we band limit? So this is Grumpy Cat, RIP. So in graphics, we have an idea of MIP maps. Basically, if you like look at if a texture is like really far away, you actually want to reduce the resolution of it. Use a reduced version of it, because you don't want to say you have like Grumpy Cat's way out in the distance and it's only taking up like 5 pixels. You don't want to like randomly sample pixels from Grumpy Cat, otherwise you'll get like a bunch of flashing as it like moves left and right, because you'll be sampling different points. So you actually want to use these like really blurry versions, which are like downsampled when it's really far away, and when you get closer, then you want to switch to the higher res version. So what we can do, we can use this process in our wavetables to generate versions of the wavetable that are downsampled at different rates. You don't want to have one for every single version, because you'll use a lot of memory, and that'll be a problem if you have like a bunch of wavetables. So we're just going to generate a few different versions to save on memory, and you can see them here. So just a quick note about this graph. You have frequency on the X, and then just the green here are just a list of our harmonics, and then you have the maximum frequency we can represent at Nyquist here. So anything above Nyquist we don't want to be playing. So these are our band limited versions. So if we take like just the fundamental, it'll be just this one sine wave, and we can see our band limited waveform at the top here. And we can, a good way to space them, a lot of people do this as octaves maybe. So you have like every mip map you go up adds another octave of harmonics into our original waveform. We don't want that because those will alias, so we drop back there. But we need to be playing any like frequencies, so I'll show you how that will work by automatically computing which mip map we should be using based on our frequency. So now we're like picking different frequencies to play, and as we like increase our frequency, we notice that it drops off a bunch of our harmonics. So one issue with this approach is that when it drops off, if you space it in octaves, this will drop down to like 11,000 hertz, 11K. And a problem with that is that if you're under 40, 50 in years of age, you'll be able to hear that like really muffled sound. So I feel like as I get older, I need to like look at the spectrogram a lot more. But I can tell you that kids like who are using a lot of synthesizers can definitely hear way up until like 18K, and they'll definitely complain if it doesn't have those harmonics. So if you want, you could reduce your spacing. So this is like every, this is my spacing. I'm changing the spacing over here. This is every octave. You can like do it every, what would that be? You can do it like every few semitones. And if you did it every, I think this is around 3 or 4 semitones. But when it drops off, it'll be more around like 17K, which could be a lot better. Okay, so that's like one approach to doing mip maps. Another approach I want to mention that a lot of synths do is they will let you alias up to a point and then downsample. So they'll do like 2x oversampling, and then you can have your harmonics extend to twice Nyquist because you'll remove that in the downsampling step. And then you can just like you could have your harmonics go like right up until Nyquist, which is kind of nice. But I just wanted to mention that because that's another common approach. I also want to mention another approach that I actually use. I'm not going to go into how often or when you should do this, but you can actually band limit on the fly by doing an inverse Fourier transform regularly. Like you can't do it every sample because it's so expensive, but maybe every 20th of a second. I don't know what I pick offhand, but I know a lot of synths do this also. And that way you can just like have all the harmonics you need like right up until Nyquist. But another thing, so the way you would store, this is more of a side note to the talk, but you would store your wavetable in the frequency domain to do this. So you wouldn't do that initial Fourier transform. You just store the harmonic version of it and then clear it out and then inverse. So I wanted to mention that because it's another type of approach, but slightly off topic. So another thing to note is you have to pick a Fourier transform library. I'm just going to put up what I chose up here just to make it easy on you, because you might want to try a bunch. You might want to try like KISS FFT or FFTW or whatever. I find that IPP is fastest for Windows and Linux on x86 systems, and then Accelerate actually has a really great FFT library. So those are the two I use. On Android, I think people use NE10. I'm not sure if anyone's an Android developer here. It's not very common for audio, but NE10 I think is pretty good from what I hear. Okay, that's all of the wavetable preprocessing that we're going to do. So next is updating position, basically just our phase, and we're going to be scrolling through that black, that original, in our original demo, that basically this black dotted line, and then we're going to be getting the sample offset and the sample position, sample offset and sample index. So let's look at another demo, because I am a visual learner, so this helps me think about it. So here we have another wavetable. These red points represent the points in our wavetable, and this black dotted line again is our phase. And we see the resolution's a little weird. Okay, so this blue point is our sample index, and then you can see like this purple like dotted line here is our sample offset. So and you can see the computed values down here. So you have our phase, which is slowly incrementing, sample index, which is just saying where we are in the wavetable, and then how far we are between the 2 points, between the blue and the green point. Okay, so that's like the basic thing we're going to be doing right now. And it's actually a really simple piece of code. I'm not going to go too much into reading code, but this is a very simple thing to do. You just increment your phase and then make sure it wraps, and then you get the sample index and the sample offset from that by multiplying the waveform size and taking the int value and taking the difference. But we don't want to use standard floor. You don't want to use the standard library for anything that's like really done not very often. So I'm not going to go too much into SIMD, but I do want to mention it because it's it'll be useful in a little bit when we're talking about really optimizing our interpolation. Basically, there's a way to convert this that we're doing into SIMD, which will do 4 oscillators at the same time. So it's a very easy, it's not easy conversion, but it's a pretty simple one-to-one. You can multiply things and sum things and take the difference between them. And this is an SSE example. And basically what a SIMD does is it will let you multiply, these 4 values by another set of 4 values, and just does it piece by piece. So the first values and the red values are multiplied together, the blue values are multiplied together, the green values are multiplied together, and then the yellow values are multiplied together. So you can translate that into SIMD here. And it's really, this looks complicated, but it's actually just a really direct translation. I'm just going to put it up there for posterity because we're not going to really talk about what each of those functions do. But yeah, it's there in case you want to translate that to SIMD. Okay, this is that was like a more simple part of the wavetable. This is probably the other big piece is that we need to interpolate our waveform because we'll be between 2 points. We need to figure out what the value is. And there's lots of types of interpolation. There's like really simple linear interpolation, and then we get into cubic interpolation, which will make it a little more accurate. And you can do higher order interpolation, which will even get more accurate to the original waveform that we want to represent. But for our case, we're just going to do cubic. I find linear to be a little too noisy. So we're going to go look into cubic interpolation right now. So if we go back to this demo, we can see some types of interpolation here. So this is linear interpolation. And you can see the black dot moving. And I want to mention, whenever it hits a point, it has a first derivative discontinuity. It changes speed immediately. And that actually creates a lot of harmonics. And those harmonics will distort our sound and will also alias. So we want to avoid having that discontinuity in the first derivative. And we want to be closer to our original waveform. So not going to do linear. Here's cubic interpolation. It's we'll do interpolate between 4 points. Can you not see? I think I can't see. There should be a faded line here or here. Let me see if I can really quickly fix that. Oh, you can see it on the right side. There's something about the color there. So you can see the cubic interpolation. It interpolates between the red, blue, green, and or everyone look over here. It'll interpolate between all four of those points. But if you look at it, you actually see the blue dot when it hits a point will sometimes have a discontinuity in the first derivative. It'll change slope immediately. And we still want to avoid that. So there's another type of cubic interpolation. I feel like I should say it ermite because we're close to, because of our proximity to France. But English speakers, a lot of times say hermite, I believe. And this type of interpolation, instead of interpolating between 4 points, what it does is it interpolates between 2 points, and then also will let you set the slope of those two at those 2 points. So if you follow this purple dot, the slope remains constant when it goes through a point, which is a lot smoother. And because we've removed this first derivative discontinuity, it produces a much less distorted sound. So this is the type of interpolation that we would want in this case. I have a little bit of confession. I've used cubic interpolation, the regular cubic interpolation in synths before, and it actually doesn't sound that bad until you get up to like really high harmonics. And then at that point, you can't even, it's like really hard to even notice. So I wanted to just put that caveat in there because I didn't even notice that it sounded bad, and I can't even really tell the difference that much when it's that many harmonics. But in some cases, it will show up. But I have to like kind of tweak it to like really hear the difference. But this is the type of interpolation we're going to use. Okay. So I'm not going to go into how to do ermite interpolation because you can just like find fast ways to do it online. This one was created by Laurent de Soras, and it's created in such a way that I edited it a little bit, but it's created in such a way that will will do it in like the minimal number of multiplications and additions, and it's a really fast way to do it. But you'll notice that it's computing 2 slopes at the top. Those are the 2 slopes. What it does is I'll go back to this really quick. The slope between, I need to pause this. The slope between at the blue point is actually the slope from the red to the green dot from the 2 adjacent points. So that's how you pick the slope at each interpolation point. And the slope at the green point is the slope between the blue and the orange dot. Okay, I just wanted to mention that because that's what it's computing. So, okay, we got to optimize that because, that's part of the talk. So we're going to interpolate this with SIMD. And remember, SIMD is doing, multiple multiplications at the same time. And in this case, we'll be doing 4 at a given moment. So once we have our sample index, we can actually retrieve 4 points all at the same time on one instruction. And you see that in like this load UPS thing. That's an SSE instruction. It'll load 4 values into a single SIMD value. And so if we're going to be doing 4 interpolations all at the same time. So when I was trying to optimize my oscillators, I was like, oh, great, cubic interpolation is 4 points. That means I can like really optimize a single interpolation because I can, use the 4 points and then multiply by the coefficients and just do one interpolation with SIMD optimization, but it's actually way faster to do 4 interpolations all in one go. And I'll get into why. I'm going to show you why in a minute, or right now actually. But so we get this matrix basically where you have our. So this is row 0 is a SIMD value, row 1 is a SIMD value, row 2 is a SIMD value. These are all SIMD values, and we get all the points we need to interpolate in the horizontal direction. But I'm going to jump back. I know this is a faux pas, but I'm going to jump back a couple slides to this interpolation code. We want each value as a separate, so we want all the first points together because that's our value 0. So we can treat it, so we can directly translate this code. But the problem is, in one value we have, instead of having like V0, 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 V0 of each interpolation point, we have all the points of one interpolation. I'm not sure if that's clear, if I'm being clear with that, but basically what we want to do is we want to transpose this matrix so we can treat each value like the first value in our interpolation is all 4 values of what we're trying to interpolate. And then we can directly translate that interpolation code. And the transposing a matrix, I thought would be really expensive, but it's actually just 8 instructions. So per interpolation is actually only 2 instructions, so it's actually really cheap. And then we can just directly translate our interpolation code into SIMD. So really the only extra bit was doing that transpose here to really getting our SIMD interpolation down, which is really just another, again, a direct translation of that earlier code. So you may, again, I want to reiterate that this is not like the most obvious optimization because it requires doing loading values and then doing a matrix transposition. And I didn't go into how slow doing a single interpolation was with SIMD. It requires doing like a horizontal add, which is pretty slow if you have to do it for every single oscillator. But this is a much faster way to do this. Okay, I have one other thing this is more of a thing to note instead of like, I'm not going to go into how to do this, but there are SIMD wrappers out there. So what they do is that value in here, so like this, M128 and this like these functions, what they'll do is they will let you treat those values like floats. So you can actually the code will look like the original here. So you can actually subtract them and multiply them together. And there's a couple versions out there. I have my own interpolation way to do this in my code, which I was thinking about branching off into its own little library, but I haven't gotten around to that. But Juice has one. It's a SIMD register. It'll let you, treat SIMD values like floats. It operator overloads them, so you can use the plus and minus and multiply. And also, Madrona Labs has also has an implementation of this wrapper. You need to be careful with compiler flags, I think, to get it so it strips away the whole wrapper. But it's way easier to write SIMD code using one of these. Just wanted to mention that because that's what I use a wrapper, and it makes code so much nicer.
I was interested that you chose to optimize within the oscillator rather than across multiple oscillators. Was there a reason you didn't process 4 oscillators, single sample per SIMD block?
Oh, I'm sorry. I think I was doing. I don't understand the question because I thought I was doing that. It just says 4 oscillators. Oh, you mean I see. You mean do each sample
Yeah, like the way I understood what you were doing there was you were processing one oscillator using SIMD.
Yeah.
And I was wondering whether you looked at it the other way of processing one sample from multiple oscillators using SIMD.
Okay, I was actually doing maybe I wasn't clear with this SIMD, or is it here? This is actually 4 different frequencies. It is doing 4 oscillators at the same time. Okay. Yeah, and we use the sample. So I'm jumping around so much, but here we are doing 4 different interpolations. I mean, it can be done if you only have one oscillator. It can be done like sample. You know, you can have like sample 1, sample 2, sample 3, sample 4 of the same oscillator. But yeah. But I was doing the 4 different oscillators, yeah.
So are those the voices, or
yeah?
Those
so it can be
the stack of oscillators or the 3 different oscillators you have in your synth, or
right. It can be. I mean, it can be a lot of cases. A lot of times unison is a very common thing. So you can just do voices in unison. It can be voices in each note you're playing. What I do in Vital is actually like I process 2 voices in stereo, so it's actually 4 values in one go with SIMD. So it's a way to so I can process 2 actual playing voices at the same time.
Hi, thanks for your talk and great visual presentation of all the material as well.
Thank you.
You talked about storing the wavetables in the frequency domain.
Yep.
And then I think I missed a little part how often you can do the inverse FFT. And could you repeat that? How?
Oh, yeah, sure. Let me see if I can jump around. I guess I was right here. But and right here. So the storing it as in the frequency domain is just is this converted values here. So you run the Fourier transform on your original waveform, and then you just store that. And then what's really cool about that and doing this on the fly thing is, like in Vital, I actually warp the harmonics while I'm doing that, so I can you can move them around and change the phase and change the amplitude. So you can actually do like weird filtering, and that's like a plus of doing it in this way. And then how often? It's really just how it's really how, you have to really measure it, how often. It's a quality versus CPU thing. I do it. I'm trying to remember. I think I do it I think I do it at 50 hertz, if I remember correctly. But I could be totally. It could be I think it's between 50 and 100 hertz, so 50 and 100 times a second.
Sure. So you do an IFFT, and then the product of that is a wavetable that you scan again, like you would if you were not doing the IFFT.
I do the IFT, and I just get the band limited version. So I basically start with this, and then I just remove the harmonics, and then band limit it, or that's the band limited version. Yeah.
Thank you. A couple more questions over the other side of the room, and then we'll go to online.
Would you be able to tell me, and for anyone online who can't ask you at the end of the show, why you don't include the phase on the final harmonic?
Sorry, the phase of the what?
Of the final harmonic, as you said you don't.
Oh, okay.
Phase. Unless it's too long of a question, I'm really sorry.
That was what do you call it? You're supposed to figure that on your own time.
I'm sorry. I'm lazy.
Okay, so so you have this. It's this last harmonic is that Nyquist is actually a Nyquist for this sample right up the top. So it'll be alternating every single sample, just up and down. But if you shift the phase, the samples just shrink in size. And then so if you convert it to the samples and then convert it back, it actually shifts back to where the peak is and the bottom peak, not anti-peak, is at every single point. If that makes sense. Yeah. Okay. Yeah, because if you shift it, convert to the samples, then shift it back, and then compute the sine wave back, the peak will be at each point. Yeah. Okay.
Hi.
Hey.
Thank you for the talk and amazing Desmos chops.
Oh, thank you. I put a lot of work into this. So
yeah, I can see that.
I hope they
I have a small question and a And I have a small comment and a big question.
Sure.
Small comment. Can you go back on the slides where you have the phase? You increment the phase.
Oh yeah.
And you wrap it around. That's just a small pet peeve of mine.
Oh yeah. Wait, which one?
Phase doesn't have to be. So you're putting your phase as a float, and then wrapping around manually.
Yeah.
There's something that wraps around automatically in computers,
right.
fixed points.
Yeah, I actually use fixed point in my code. I didn't want to say like you needed to do that. And it's like a little more.
We should start doing this because people don't use fixed points enough, I think.
Yeah, fixed point is actually real. I actually had this in my talk originally about how I do fixed point. But yeah, if you just represent it as an unsigned integer and your delta phase as an unsigned integer, you don't need to wrap it. And here you'll be doing like instead of multiplying, you'll be doing a bit shift to
and
get,
then you don't
get the sample position
and then you don't have to convert from float to int when you're hitting your buffer.
Right. I was worried about time, so that's why I did something that was more familiar. But
good.
Yeah.
The question is, so from the continuous waveform that you're drawing and the output of your synth, you're doing two successive approximations, right? You're band limiting, not exactly at Nyquist because it depends on your MIP mapping step.
Okay.
And then you're interpolating between points, which is also imperfect because you're not using, you don't have infinite time, right?
I would say that the MIP map is actually not really an approximation. It's actually accurate, but maybe you are removing some of those harmonics at the top. But if you can't hear, I mean, if it's above 20
Yeah,
20.
okay. It's just, I know it's small details, but...
and I do it on the fly, so it would go up to the last harmonic that you can hear. If you do it on the fly, you can just put the cutoff anywhere. So then it would just go right up to Nyquist.
Either on the fly, or you have to choose very small steps in your MIP mapping process.
Or you can do the octave and then do double 2x oversampling and then do the downsample.
Yeah.
That's what I originally was doing, but I switched to the on the fly thing.
So the question is, you have these two operations. Do you have any insights on how you could do it in just one step, like super interpolation that takes the speed into account, the frequency into account?
I mean, you can. I've thought about this. You can actually you can probably do an FIR filter and interpolation at the same time. I don't know how to compute those quickly enough or do them well enough to get the filtering and the interpolation and like not use like a bunch of points all at the same time. If you know something better, like let me know. But
a little bit, but
okay. Well, we'll talk later. Yeah.
So, say you want to approximate some function you have with a cubic B-spline.
Okay.
Then one way to get the control points for the spline will be to just sample the function different points and then use those points for control points. That would be like what you're doing now, right?
Sorry, I'm going to go back to... I don't know if I understand your question.
So you have some function, you want to approximate it with like a cubic B-spline,
Yep.
One way to get the control points is just to sample the function at like different intervals and then use those samples as control points.
Yep.
But if you want your spline to fit the function more... like minimize the overall round mean square error.
Yep.
You would use something like least squares method to nudge your control points up and down so the spline will fit better, right?
Right. Mm-hmm.
Would this be applicable to what you're doing here?
Yeah, I think if your goal is to minimize the error of your offset, but I find that actually removing first derivative discontinuities is a little more important than getting a more accurate waveform. Yeah, that's something that's actually a lot of very common in a lot of approximations. If you're doing like doing power of 2 approximations or log approximations, you want to keep the you want to make it as smooth as possible, keep as many derivatives 0 as possible over then you prefer that than being more accurate.
All right. So then, second question: you use Harmonix cubic splines.
Yeah.
So what about using cubic B splines since they are C2 continuous?
Wait, cubic B splines. Wait, is it C? So it's continuous in how many derivatives?
I think the cubic B splines you can derive 2 times.
Okay,
they're smoother than the Harmonix splines.
So does it interpolate?
No, that doesn't go through the points.
Okay.
That's the caveat. So that's why I use least squares method to notch the control points.
There might be a better way to. Yeah, I haven't really gone into other types of interpolation. You might want to try that. I'm not quite sure. So
right.
it might be.
I was just curious because we use B splines a lot, but you need to notch the points when you use them.
Right. All right. Thanks.
Thanks. I think we've got 1 or 2 more online. Okay. From Marion, could you get away with linear interpolation if your waveforms were higher resolution time-wise?
I mean, you still get first derivative discontinuities, which will create distortion. And I find, if you could create a bigger wavetable, you could be, missing more cache, getting more cache misses. Cache misses are like kind of a black art for me in terms of optimization. I kind of just think trying to minimize the amount of memory I'm accessing. I find that a slightly better interpolation is better than just doubling your waveform size. But if you find something else, then you can let me know.